Okay, hello and welcome everyone to our Vox Days Romania talk. We are really glad to be here together with all of you. Let me dive right in and start this talk by showing you a picture. So what we actually see here is a pretty interesting and memorable phenomenon we find in the wild. It's a big tree and it's wrapped in some other species of plant, and they are called Strangler figs. And the special thing about these plants is their growing behavior upon their host trees. Now, usually these strangler figs, they seed in the upper part of their hosts, and then they primarily grow from top to bottom. Eventually, they root in the soil themselves, and over longer periods of time, and this is what we actually see here, they are able to fully envelope the original tree structure, which effectively means that they are slowly but steadily killing their host trees. Now, the reason why I'm telling you that is because we can mimic this particular growing behavior. We can transfer that in a technical context. And what we want to show you today is how you can apply a pattern called the Strangler fig pattern, which is most often attributed to Martin Fowler, to a software migration project. Now, before diving in, let me briefly introduce myself first. So my name is Hans-Peter Grahsl. I'm currently working as a part-time trainer at a company called Netconomy, where we are building large e-commerce solutions for our global customer base. Being part-time means I have some time left for other things. And here I am also working as an independent engineer and consultant, and help clients to build event-driven architectures, mostly using messaging or event streaming platforms such as Apache Kafka, and combining that with non-relational data stores such as MongoDB. I'm really excited to be here today and share this virtual stage together with my good friend from Hamburg, Germany, Gunnar. Maybe you introduce yourself briefly.
Oh yeah. So hey there, I'm Gunnar. Nice to be here with you, Hans-Peter. Well, I work as a software engineer at Red Hat, and I'm the engineering lead for a project which is called Debezium. And Debezium is a tool for change data capture. So we will get to learn about this in the talk today. There's a few other open source efforts I'm involved with. Maybe you've heard about Quarkus. I've contributed a few things there. I've been working on bean validation 2.0, and yeah, I just generally love doing open source. Hans-Peter, back to you.
Yeah, thanks, Gunnar. So let's dive right in. And I think if we imagine how software migration projects are done, you can imagine at least that this is sometimes very, very challenging, given a reasonably large and complex system that we want to migrate. And let's say we want to migrate an old legacy application, typically a monolithic architecture, into microservices. And if you happen to have taken part in such a migration project, and if this project was tried in a hard cutover approach, chances are that it didn't end well. Now, the reason being that so-called Big Bang migrations, they are not often just only costly, they are really literally very, very risky, and are oftentimes even doomed to failure. Now, this is exactly where the Strangler fig pattern comes to the rescue that we want to discuss with you today. It should help us act differently and hopefully do a better job when we try to migrate, for instance, from one application architecture to a totally different one. And on a very high level, this Strangler fig pattern is composed of three phases. First, you would decide which part or which parts of the functionality of your existing system you want to extract. For instance, you want to extract that into a separate microservice. Then, of course, having one or multiple services that are extracted and you still have some functionality in the monolith, you need to find a way that this can coexist. So you need to run those services and the monolith in parallel so that they can collaborate. And then when you, all those components that you have migrated successfully, you could at one point then safely eliminate from the monolith. And this is exactly what we are going to discuss also today. And we even try to show you a demo application that you can run and test afterwards on your own as well. But before, let's briefly summarize again, what is the overall goal? Why should we want to do it that way? So the reason being that we want to find a smooth migration path. We want to respect this evolutionary nature that comes along with migrating one system into the other one. And again, the reason being Big Bang migrations don't work so well. At least this is what experience from the practice has shown us. Now, before looking at a concrete example to better understand how this pattern can be actually applied, I want to hand over to Gunnar, who gives us a short introduction into open source change data capture with Debezium. Gunnar, over to you.
All right. Thank you so much, Hans-Peter, for this nice intro. So let's talk a little bit about change data capture, what it is, and what Debezium does in this context. And well, the idea really is very simple. Essentially, it just means you have data in your relational database or in your NoSQL database. And now whenever something changes in your data, so a new record gets inserted or something gets updated or something gets deleted, you would like to be notified about this data change, and you would like to be able to react to the data change. And this is exactly what CDC and what Debezium does. So it taps into the transaction log of the database. So all the databases, they have a transaction log, an append-only log, where they essentially persist the data as the user modifies data. Debezium uses this transaction log as the source for change events, extracts them, and sends them out as uniformly formatted and represented events to consumers. Typically, this is done via Apache Kafka. So we have Kafka in the middle there as a means of transportation and as a means of decoupling. And this gives us some very nice guarantees or let's say semantics, because our event producer, which would be the database and Debezium, and our consumers, they are decoupled, right? So let's say one of the consumers isn't running at a particular point in time. Well, once it comes up again, it can continue to read the topics with the change events from Kafka at the point where it left off before. So this is generally the way you would go about CDC. For short, change data capture with Debezium. So it runs in conjunction with Kafka. And in particular, it runs as a plugin or as a set of plugins in terms of on top of Kafka Connect. So Kafka Connect, it's a part of the Kafka umbrella, and it provides us with the ability to run source connectors like Debezium, which take data from some external place into Kafka, and then sync connectors like this Elasticsearch sync connector or one for JDBC, or there's sync connectors for any kinds of systems, and they will take the data from Kafka and send them to your search index, to your cache, to your data warehouse, wherever you want to have the data. So that's the general idea. So, and now Debezium implements CDC. So it's an open source CDC platform. So this means it's Apache licensed. It's all free for you to use. And what I'm very happy about is there's a very vibrant, a very active community around it. So we have more than 300 people who have contributed to the project up to this point. So it's very, very healthy and active project. And really, the idea is not only to give you this core CDC functionality, so to extract changes from some transaction log, but also to provide you with a full, complete CDC platform. So for instance, there's things like snapshotting. So this means when you start up a connector, optionally, you can have it take a snapshot of the current data as it is in the database. The reason for doing so is, well, you might not have the transaction logs from, let's say, last year. And still you would like to start your change stream with an initial consistent version of the data. So this is where snapshotting comes in. There's things like support for the outbox pattern. So we won't go into much depth about this in this talk, but the outbox pattern is a very useful thing if you want to even more decouple your event source and your event consumers in terms of the event format and event schema which you exchange. And one of the newer things which we just added is a web-based UI. So far, all this was essentially just REST-based configuration, and now just recently we added this Debezium UI, which allows you to visually go about setting up connectors and operating them. And lastly, there's quite a few really significant large installations of that. So I'm aware of users which use Debezium to stream changes out of hundreds or even thousands of databases. So it's really battle proven. In terms of the connectors, now the thing is, there is not one standardized way how you could go and extract change events from the transaction logs of all different databases. So instead, we need to implement a bespoke Debezium connector for each database, which we would like to support. But then the good news is you as a user, you don't have to think about that too much because the event format, which we will see in a bit, that's largely an abstract format, which means as an event consumer, you don't have to care, does this event come from Postgres, does this event come from MySQL, and so on. But we as a Debezium team, we need to implement those connectors. Of course, we try to share as much code as we can between them. And well, there's a growing number of connectors, as you can see here. Some of them are stable, which means their event format is really proven. We don't change it. And then we also have some incubating connectors, which are still in flux. So there it might, for instance, happen that the specific representation of, let's say, one particular data type, it might change. And another very interesting development related to that is that we also see people or companies, projects which are not even part of the core Debezium umbrella, that they also use the Debezium framework to implement CDC connectors. And one example for that would be ScyllaDB. So let's say Cassandra compatible NoSQL data store. And they use the Debezium framework to implement a CDC connector, which then again shares the same format as all our other Debezium connectors, which makes it very easy for you as a user if you have this sort of polyglot data persistence environment, which I believe most or even all users have. Now, I mentioned most of the times people use Debezium with Apache Kafka and Kafka Connect. And now when I say most of the times, this also implies there's some cases where that's not the case. And this is true. So you also can use Debezium in other ways. And there's essentially two more options which you have. One of them is you can use it as a library embedded into your Java-based application, which means you just, you implement a Spring Boot application, a Quarkus application, whatever you have. You embed Debezium into that, and then you just register a callback method, which should be invoked for each change event which comes in. And then you can react to the change event in any way you want. So that's a very powerful option for using Debezium. It's oftentimes used by integrators. For instance, in Apache Flink, they use the Debezium embedded engine to have a very slim and very efficient integration of Debezium into Apache Flink. In the third mode, how you can use it, so we have Kafka Connect, embedded engine. In the third mode would be Debezium server, and this is what we see here. And essentially, that's a ready-made runtime which takes the Debezium connectors and makes them available for usage with other messaging infrastructure other than Apache Kafka. So sometimes, or maybe you are, for instance, on Amazon Kinesis, or you're on Google Cloud PubSub, you're using Apache Pulsar, all those kinds of things. And now you also would like to benefit from Debezium's CDC capabilities, and this is what Debezium server lets you do. All right. So then let's talk a little bit more about the actual change event. So what is in a change event? And well, if you know Kafka a little bit, and it's the same for the other messaging infrastructure, really, you will know messages there, they have a message key, which defines the routing and in particular the ordering of messages, and the message value. And the message key in case of Debezium, that resembles the primary key of your tables, or I should say your records. So all the change events, which for instance pertain to customer 123, they will all have the same message key. And this means the change events, there will be the correct order guaranteed. So a consumer will see all those change events for that particular customer or for that particular purchase order and so on in the same order as they were produced by the database or as they were created in the database. Whereas you would not have necessarily a global ordering across the change events from all the customers or from all the purchase orders. But typically, that's not what you need. So that's the message key. And then the message value, it's a structure which we see here, and we can explore it a little bit more. So first of all, we have this before and after part, and they essentially describe the old state of the row, which was changed here, and the new state of the row. And now within before and after, you can see it here, there's a structure which resembles the actual table definition. So for each column in your table, you would have one field in those before and after blocks. Now, of course, if for instance, this would be an insert event, there wouldn't be a before block because, well, we just have a new row state. But for an update, as you see it here, you would have both before and after. And then, in addition, there's some further metadata, which we see here in this source block. And this tells you this gives you some useful information, like what's the connector which produced this event, some sort of timestamp. So when was it processed in Debezium? What's the table where this is coming from? Maybe the query which caused the change. Sometimes we can get that position in the log file, transaction ID, those kinds of things. You also get this operation discriminator, which we see here. So in this case, it's you as an update, which tells you, okay, what kind of event this is. And now this is the semantical structure. And as a sort of an orthogonal concern to that, there's the question how those events get serialized. So in Kafka, everything is just essentially a byte array. So we need to think about how we take this semantical structure and serialize it into bytes. And this is where this notion of message converters comes into the picture. So you can convert those messages, for instance, using into the JSON format, into Avro as a binary format, and so on. So really, this is you have some flexibility there. All right, so that's the BSU in a nutshell. I hope I could give you a little bit of an overview of what it does and how it works. Now, Hans-Peter, over to you, and I think you can tell us how we can actually use this for this application migration using this Strangler fig pattern.
Yeah, thank you, Gunnar. So let's look at a concrete example to better understand how CDC nicely supports this idea to propagate changes back and forth between systems. So what we see here is a fictional application. It offers functionality for a pet clinic. It's deliberately based on an old technology stack. So we just pretend for now that this application was written and never updated ever since then. So it still uses Java 6, Spring Framework 3. It's a monolithic application architecture, and we want to now migrate it over to microservices. So let's say we want to start our migration with the owners component. But as a very first step, we would introduce into this architecture some kind of proxying mechanism. Now, the proxy will serve us for the purpose that we can then, while we have to support that coexistence, nicely route different types of requests back and forth between either the microservice world or the monolith. So in the first step, of course, this proxy just routes all traffic, all reads, all writes still to the monolith, and this serves every user request. Now, we would decide to migrate and start this migration effort with the owner component, which is shown in the left most square here on the picture. And let's say we implement this microservice then in a more modern stack. In this case, it could be a Quarkus application running Java 11, or it could also run even Java 17. And let's say we do that also not in one go, but we say we want to first only use that microservices to support read requests for this owner's functionality. And then once that is implemented, the question, of course, arises, how do we source the database, the dedicated database that backs this microservice? And this is where we are now leveraging a change data capture pipeline. And we could do that, for instance, by using a MySQL source connector from Debezium, configure it properly so that it listens to changes that are relevant for this owner service, propagates those changes into corresponding Kafka topics. And from there, then, we could configure a sync connector, which writes the data into the target data store. In our case, this could be a document database such as MongoDB. Again, when we are at that point, we can make sure that this microservice application can serve all reads. Of course, any changes that are happening will be continuously captured and propagated by Debezium. So it will do an initial snapshot of everything that is there, and then it will give us all future changes. Now, if we want to extend that and also support write scenarios, we, of course, need to implement those write functionalities first in the microservice. But once that's done, we can reconfigure our proxy once more so that the write requests for the owner-related functionality are also routed to the microservice, and everything else is still served at that point then by the monolith. At that point, when we say we have migrated all the owner's functionality into its own service, we could then also eliminate that component from the monolith, or we can leave it there, it's just not used anymore. Now, once we do writes on the microservice side, of course, the question arises, how does the data find its way back over to the monolith? Because, of course, other components in the monolith, they might need to access those changes. They might need that to work properly. So we have to find a way to propagate changes back. And this is where we first would, of course, update the MySQL connector to stop listening for changes of owner-related data in the monolith. And then we configure another change data capture pipeline into the opposite direction. So in this case, we could configure another Debezium source connector that now listens to changes in MongoDB collections. And every time the microservice does writes or changes into those collections, they are again propagated to Kafka topics. And from there, we could send them further using a JDBC sync connector that inserts and updates into the corresponding table structure of the monolith. For now, that concludes this discussion of that example. We will later come back for that in our live demo. But let's take a closer look at this bidirectional change data setup. And here I want to hand over back to Gunnar, who will discuss a few of the subtleties that we might want to keep in mind when we do such change data capture scenarios.
All right, exactly. Thank you. So yes, we have seen how we can use the Strangler fig pattern and in particular the surrounding approach for gradually moving functionality from a monolith over into multiple microservices. But now, if you think about it, you might have some questions. So for instance, you might ask yourselves, hey, are we not leaking our data model from the monolithic database into the microservices? How would we go about building what we call aggregated structures? So in case of Debezium, each table in your source database will reflect or will be corresponding to one topic in Apache Kafka. And maybe you would like to actually join the data from multiple topics and have an aggregated structure, or in domain-driven design terms, a root aggregate and all the things which belong to it in a single document, which all then are sent to a single topic. So that could be a concern. And lastly, there's also a question, so how do we actually go about transaction boundaries? So we may update multiple records in our source database within a single transaction. So let's say we insert one owner and multiple pets into a single within a single transaction. And now the question is, can we achieve it that we process and consume all those events which originate from one transaction all at once? So can we do some sort of buffering? So all those are very valid questions, and we will see how we can go about in addressing them. So now, first of all, let's come back to this very basic C2C pipeline here, and let's think about this aspect of leaking the internal data model. And this is certainly a valid concern. So you might wonder, hey, if I'm going to change the names or types of my source tables, then would that impact me? Or how will this be reflected in the consumer? And there's different ways how you can go about this. And the one which would be the simplest in terms of Kafka and Kafka Connect is to use what's called SMTs, single message transformations. Those SMTs, well, as their name tells you, they are applied to each and every message one by one as they either are sent into Kafka or as they are taken out of Kafka. And then you can do things like, for instance, renaming columns or filtering columns, changing their types and so on. So let's say you are just not happy with the names of your old data model. Well, you could use such an SMT to use more appropriate column names going forward. Or you could use such an SMT to adjust the types, to massage the data, to filter out columns. You could also do that, and so on. So that's SMTs. Now, and of course, well, as I mentioned, you can apply them in the source and on the sync side, right? So there's good reasons why you might want to do it on either way. So typically, if you say, okay, this is a legacy data structure, which is my database, I don't want to expose it at all to the outside world, then you would apply it on the source side. So the data will be modified before it even is sent into Kafka. But then maybe you also have a case where you are applying some specific transformations just for one particular consumer. So maybe you have specific naming requirements or specific type constraints which are just applied to, or which just apply to one particular consumer of the data. Well, then you can take such an SMT and apply it on the sync side, and then you could implement different transformations for different consumers. So you have some interesting options there. So now, as I mentioned, SMTs, well, it's single message transformations, right? So they will process each record one by one. And this is useful for things like filtering, renaming, modifying types, and so on, or maybe adjusting date formats. That's another good example. So maybe you have some sort of legacy date and time format in your database, and you would like to normalize it. So you can do all those kind of things very well with SMTs. But then things are getting more interesting, even if you think about some more complex stream processing. And this is where this example, which we discussed with the aggregates, comes into the picture. And we will see how it looks like a little bit in the demo. So you could use something like Apache Kafka Streams or Apache Flink for implementing stateful stream processing. So you can essentially, for instance, take the data from multiple topics and join the data so that you, for instance, would have what would be represented as a 1 to n sort of relationship in your database, and you could take that and join all the data from such an aggregate into a single document. Or you could think about using stream processing, and in particular stateful stream processing, for implementing some sort of buffering, which essentially awaits all the messages which are originating from one transaction in the source database and only sends them out at once all those events have been, for instance, arrived in Kafka. The way of doing that in Debezium is there's a specific metadata topic which gives you information about transaction boundaries. So it tells you, okay, in this particular transaction, those 5 records of this table type have changed. Another 3 records of that other table type have changed. And you can use this metadata information for implementing such a buffering logic, if you will. All right, so now let's show you some of those things in a demo, and I have prepared a video for that, and I'm going to play that back. I just need to go here and here, and this exactly takes this pet owners example, and we will see how we can implement this Strangler fig pattern. So now this all is running in Docker Compose. By the way, the source code, it's all on GitHub, and we will have the link for you. There's a few things running here. So there's Kafka and Zookeeper as a stream or as an event streaming platform. There's our monolithic application. That's the Pet Clinic one. It uses the MySQL database. We have Kafka Connect, which runs Debezium. We have this K-Streams table joiner application, which does this joining from multiple topics into one. And of course, there's also the Quarkus owner service. So that's our newly extracted microservice. And lastly, we have this one uses MongoDB, by the way, as the data store. And lastly, we have Nginx as this routing component. So now let's go to the old application. And what we want to do here now is we would like to extract the owners part of that. So this is how it looks like. And now the data still is in MySQL. And well, this is how this search functionality looks like there, right? And in particular, we have also those pet this pet data there. So that's in another table, and there's this sort of 1-to-n relationship between them, right? So one owner can have multiple pets. So that's the data we would like to take and move it over to the new Quarkus-based microservice. All right, so a little bit ahead of time, so let's see what's going to happen. But essentially, the next step will be to set up the well, first of all, we need to set up this routing component. So this is what's going here. Could show you the Nginx configuration, but it's not too exciting. But really, what it does is it just takes now the read path, which would serve those read requests for owners, and routes them now over to this new microservice. So if we go to the search path again, we will automatically be routed over to the new microservice. And of course, now we don't have any data here. Well, because all the data still exists only in the monolithic database of the old service, right? And now we need to set up the Debezium connector, which will take the data from that MySQL database. So it's an instance of the Debezium MySQL connector. We are just interested in those 2 tables, owners and pets. So we have the ability to limit our CDC process to just some tables. So that's what we are interested here in. And then we use, in this case, JSON as the event format for the message keys and also for the message values. So everything will be sent out in JSON. And of course, there's more information in the config, like the database, the credentials, and so on. So that's how this data then looks like in this Kafka topic for the owners. So here I see, okay, I have, by the way, that's what we call a snapshot event. So you can see it because it has this op type R, so read, it's a read event. And now we will have for each owner in the database, there would be such a read record here in this topic. And that's why you don't have this before block. This will be empty for a snapshot event. In the after block, you will have the data for the owners table. And then we have this source block, which we discussed with all the metadata like table name, position in the log file, transaction ID, and so on. The pet topic would look similar, so it's not too exciting, but we also can take a look at the joined data. And I'm not going to show you the source code of the stream processing application because it would lead a little bit too far, but we can take a look at how the data in this joined topic looks like. So it's pretty much what you would expect. So now this is a nested, a complex structure, and it essentially has, well, substructures for the owner's data, and then also an array for which contains an entry for each pet which belongs to that owner. And then this Kafka Streams application, whenever either something changes on the owner side or on the pet side, so maybe a pet gets added, for instance, it would recalculate that join, and we would see an updated document of the particular owner and all their pets in this joined topic. And now, as we are going to sync that data into MongoDB, this is, of course, very interesting because in MongoDB, we can get a single document with all its data by just a single lookup, so we wouldn't have to do any join. So that's very interesting. To do that, we also need to set up the sync connector. So that's what we see here. That's the MongoDB sync connector. And in this case, well, it subscribes to that topic with the joined data, and it does some transformation. So we can, for instance, rename fields here. So that's what's happening. And it's also, it generally could just say it's massaging the data a little bit, and then it will take, it also prepares the keys, for instance, so they are in an expected format, which we would like to have in MongoDB. And each of those documents will be stored into a MongoDB document. And with that, Hans-Peter, I'm handing over to you, and you can walk us through the rest.
Exactly, thanks. So let's see if this data propagation is really happening. And for that, we would go to the web UI of the microservice, refresh that, and indeed the data will be there, as we have just seen, thanks to the change data capture pipeline that we set up. Now, let's see if also future changes will be propagated. And for that, we want to change the data in the monolithic application. So we go back to the monolith, and we try to take one of the owners there and change the name accordingly. So we will be presented this edit owner form here, and then we change the name, in this case, to George Jr. Franklin Wayne. We will save it. Of course, it will be saved locally to their own database of the monolith, MySQL. If we find that to take the read view look in the microservice, we see, yes, the name change has been propagated. Also, let's see if we can do that for the pets data. And again, if we would change those pets in the monolith, this will re-trigger this join operation that we have seen that is done by the Kafka Streams application behind the scenes, because it needs to join those changes together that are sent into separate topics. And if we change that to Neo, so the pet is now called Neo, let's verify what happens regarding the change data propagation in the microservice side. And again, if we refresh that, we see the name is now Neo. Now, taking this one step further, we can also say we want to support now the write path on the microservice side here. And for that, of course, to work, we would first need to go back to reconfigure also the proxy so that it will present us with an edit form that is then served from the microservice. So we will change this proxy configuration, and once then the proxy is up and running again, it will reroute those requests, of course, to the microservice. Now, if we go to the microservice, we can edit a particular owner with the data there in this form. But before doing that, we would need to make sure, of course, remember what we said earlier, to only have a single source of truth. So writing this data only at one of those sites, microservice or monolith. And for that, of course, we need to first reconfigure the CDC, change data capture pipeline, the MySQL source connector accordingly, so that it stops listening to changes for owner data. And we see that here in the configuration pretty nicely. It does now is it cares for changes in one table of that pet clinic database, which is the pet clinic pets database. So those are still written there, but it stops listening to owners. And then we can configure the source connector for MongoDB, because now the owner's data gets written on the microservice side. We need to capture it also from there and send those changes to Kafka topics. And we reconfigure, so we configure that then, the source connector in a proper way, but this is not sufficient then. we also need to make sure then that this data that is firstly written to Kafka topics will then eventually find its way also back to the monolith. And for that, we configure then another JDBC sync connector, which takes those changes from MongoDB and then writes it into the corresponding table structure. And if we do that, we can, of course, change the name back on the microservice side to what it was originally, update that there, and we can verify again then if those changes are really propagated back to the monolith. So if we take an edit form here in the monolith's UI, we can see the corresponding owner data. And if we do that for a pet, we see again, okay, the name has changed back now also on the monolith side to what it originally was. And this actually pretty much concludes our demo. Again, the link will be there for you to try it out on your own. And this is, I think, hopefully makes the case how change data capture and this, especially this bidirectional data propagation scenario can be nicely supported, in this case by Debezium and change data capture. With that, I want to hand back over one last time to Gunnar to wrap it up.
All right, Hans-Peter, again, thanks. So as you say, let's wrap it up. We have seen how this works in practice. And I hope we could make the case that thinking about such a monolith to microservices migration in terms of the Strangler fig pattern comes with a few advantages. And well, the most evident advantage is, of course, you do this in an incremental way, right? So you can think about it in terms of baby steps, if you will. So instead of having this one big bang migration, you can take one piece of your functionality at a time. And this, of course, reduces the risk, right? So for instance, you could also think about maybe moving over to multiple implementations of the same functionality to do some sort of A/B testing. So you have all those options there. You can pause this migration. So maybe priorities shift. You cannot continue on this path for some time, or maybe you need even to stop it. Well, in this using this gradual approach, you have again this option to do this. And in the worst case, you even could go back, right? So maybe something is wrong with the newly built microservices. We don't hope so, but it could happen, right? Well, you could even then go back to the monolithic application. Of course, there's some subtleties you need to think about in terms of your data, but you can do it. And well, the underlying point of all that is, this is there to minimize the risk of such a migration, right? So don't think about it in terms of one huge big bang cutover operation, but it's there happening gradually to minimize the risk. Lastly, a few resources for you. So as I mentioned, Debezium is an open source project, so you can find all the information on the website, debezium.io. This has, of course, all those connectors which we've seen. If you would like to know more about the MongoDB sync connector for taking data out of Kafka into MongoDB, then you can go to the MongoDB website and learn more about this particular sync connector. Again, as part of the Debezium organization on GitHub, we have a repository with tons of examples. So you have examples for the Strangler fig pattern, but also for other things like the outbox pattern for implementing distributed sagas using change data capture. Just showing you how to use CDC events for putting data into distributed caches and all kinds of things. So there's tons of examples in this repo. And lastly, the link to this particular Strangler fig implementation, where you also would, for instance, can find the stream processing application, which we haven't shown you here. So you will all find that in the last repo. And with that, we are done. Thank you so much for attending this talk. I hope this was interesting and you could find something new and exciting in it. And we will be very happy to answer any questions which you may have.
Wow, thanks so cool. Thank you. Thank you, guys. There's a question. It is possible to have the Git link for the clinic. You shared the links, but I'm sure that you're going to tweet about the presentation, where's the deck, and people can get the deck and afterwards look into that. So please be looking after the tweet, probably having Vox Days Romania in it, and with a link to the GitHub, because I'm also interested in that. Well, Congratulations, guys. I mean, you've really built like a not only a migration story, but you actually built a real migration of an app. So
cool.
Really
so
nice and cool. I would love to chat more with you, but unfortunately need to wrap it up on this track and to direct people